When you first learn about radiation, it's always alpha, then beta. One is stopped by paper, the other by foil. But then there's this third one, the mysterious one that just powers through almost everything.
That would be the gamma ray, symbolized by the Greek letter gamma, of course. And you're right, they are, by far, the most penetrating form of electromagnetic radiation we know.
So for this deep dive, I guess we're charting their journey.
Yes.
From these, huge cosmic events all the way down to how we use them on Earth.
Exactly. From the universe's most extreme origins to some surprisingly beneficial solutions right here at home.
Okay, so let's start at the beginning. Who figured this out? It wasn't immediately obvious, was it?
Not at all. A French chemist, Paul Viard, first discovered the radiation back in 1900. But it was actually Ernest Rutherford who gave them their name, gamma rays, a few years later in 1903.
And he called them that because of their penetrating power, right? To kind of complete the set, alpha, beta, gamma.
Precisely. It cemented them as the third and most powerful type. And that power is directly tied to their incredible energy.
What kind of energy levels are we talking about here?
We're talking photon energies from around 10 key, which is already high, up to levels exceeding 10 to the 11th key. It's just immense. And the modern distinction, from X-rays isn't just the energy level, it's the origin.
The origin.
Yeah. For it to be a gamma ray, it has to come from an atomic nucleus or from particle decay or annihilation. It gives us a window right into nuclear physics.
So when we look out into space and see gamma rays, we're literally seeing the universe's most violent and energetic activity.
Exactly right. They're signatures of things like pulsars, those are the rapidly spinning neutron stars,
right,
and quasars and active galaxies where matter is just spiraling into a supermassive black hole.
Okay, but you mentioned the most spectacular example.
Ah, yes. That would be the gamma ray burst, or GRB.
That sounds like something straight out of science fiction.
It might as well be. They are the single most intense electromagnetic events known to exist.
So what causes them?
Things like hypernovas or two neutron stars colliding, and the power output is, well, it's hard to comprehend. A long-duration burst, which might last only 20 to 40 seconds.
Just seconds.
Just seconds. It can release about 10 to the 44th joules of energy. That is the same amount of energy our sun will produce over its entire 10 billion year lifespan.
I don't even have a word for that. That's just unbelievable.
It is.
And yet we also get them here on Earth, don't we? Just not quite as powerful, I hope.
No, thankfully not. They occur naturally from the decay of isotopes like potassium-40 in the ground and even from cosmic rays hitting our atmosphere. Sometimes you even see flashes associated with lightning.
So with that much penetrating power, shielding must be a huge challenge.
It is. It's a complex engineering problem. You need materials with really high atomic numbers and density. We're talking thick lead, dense concrete.
Right, those are the classics.
And lead is about, say, 20 to 30% more effective than an equal mass of something lighter, like aluminum. It's all about that density.
Speaking of needing the right tools for complex problems, whether it's high-energy physics or the challenges in business today, you need sophisticated solutions. This deep dive is brought to you by our sponsor, Embersilk. If you're looking into AI training, automation, or uncovering where intelligent agents could make the most impact for you, check out embersilk.com for your AI needs.
That's a great point, because our ability to actually tame and use this power is, well, it's one of modern science's great achievements.
Absolutely. We've turned that incredible penetration from a bug into a feature. In industry, for example.
Oh, definitely. We use isotopes like cobalt-60 and non-contact sensors. They can measure levels, density, and thickness in things like refining or food processing without ever touching the product.
And that leads to food safety too, doesn't it? Irradiation.
Yes. We use it to sterilize medical equipment, which is critical, and also to preserve food by killing off bacteria or preventing vegetables from sprouting. It keeps them fresher longer.
I think, though, the most incredible application has to be in medicine.
I would agree, especially in cancer treatment. The gamma knife is just a brilliant application of physics.
How does that work? It sounds so intense.
Well, instead of one giant, powerful beam, it uses hundreds of weaker beams.
Okay.
And they're all aimed from different angles to intersect at one single point, the tumor. Individually, the beams are harmless to the healthy tissue they pass through.
But where they all meet?
The combined dose is lethal to the cancer cells. It's incredibly precise and minimizes collateral damage.
And we also use them for diagnostics, like P-scans.
Exactly. Positron emission tomography. The tracer we introduce emits positrons, they annihilate with electrons and produce gamma rays. And those gamma rays light up areas with high metabolic activity, which can show us where cancer is.
It's truly become a cornerstone of modern healthcare.
It has, and if we look back out to the cosmos one last time, astronomers actually use high-energy gamma rays from very distant quasars as a kind of cosmic measuring stick.
A measuring stick for what?
By studying how those rays travel through the vastness of space, we can estimate something called the extragalactic background light. It basically allows us to learn about the entire history of every star and galaxy that has ever shone. We're using this penetrating light to read the universe's own story.
That is an inspiring thought. Using the universe's most intense light to shed light on its own history. If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.